Now proceed to question 3. The oxidation rates according to the equation 2C2H with O2 give 2C2O. The reactor contains 100 kmol C2H4 and 100 kmol 2. Which reactant is limiting? What is the potential excess of the other reactant? If the reactant proceeds to combustion, what is the extent of the reaction? How much of the excess reactant will be left? And how much C2H4O will be formed? Okay, let's solve the first part of this question first. Okay, so in the question we have C2H4, so we write 100 kilomole, and then we have 100 kilomole 2, so 100 kilomole O2. Okay, so if you look at the ratio of this equation where we have C2H4 to O2 is 2 to 1. In other words, okay, if we have 100 kilomole of O2, okay, we need to have 200 kilomole of C2H4. Because we have 2 times with 100. Here we have 1 times with 100. 1 times with 100 we get 100 kilomole. 2 times with 100 we get 200 kilomole. So in this question, which reactant is limiting? Since we only have 100 kilomole of C2H4 in the reaction, in other words, the limiting reactant is C2H4 because we only have 100. We require 200 kilomole. Okay. Second part of this question is what is percentage excess of the other? So the other reactant means O2. Okay, O2. Before that, let's go back to our lecture notes where we have fractional excess of A equals NA feed minus NA stoichiometry over NA stoichiometry. So what we need to do now is to solve. So we have the formula of fractional excess. And since we know that O2 is in excess, so we put NO2 feed minus NO2 stoichiometry over NO2 stoichiometry times with 100 because we need to find the percentage excess, so we need to time with 100%. So it will be feed is 100 kilomole, okay, 100 kilomole minus, okay, we know that we need to use 100 kilomole of C2H4, so in the reaction we need to have 50 kilomole of O2 based on the stoichiometry ratio. Okay, so we minus with 50 over with 50 and then times with 100%. What we get here is 100 minus 50 is 50. 50 over 50 is 1, so 1 times with 100 is 100%. Okay, so the answer will be 100%. Go to the last part of this where we have if the reaction proceeds to completion, what is the end of the reaction of the excess reactant will be left, how much C2H4 will be formed. In other words, for excess of reactant we need to find O2 left because we know that O2 is in excess, and also proceeds to completion means C2H4 is finished. Okay, where if we use extent of reaction formula to solve this question, so we know that we have minus 2 epsilon for C2H4, then we have minus 1 epsilon for O2. Why minus 2? Because it is being reacted, or it is consumed in the reaction. And y minus 1, the same goes to O2, it is consumed in the reaction. And we have plus 2 epsilon for C2H4 because it is being produced in the reaction. Okay, initially we have 100 here, okay, for C2H4, and then we have 100 for O2 and 0 kilomole for C2H4O. Then we need to find the final amount of each component in the reaction. Okay, first thing first, how to find the extent of reaction? So we need to refer to the product that is being consumed completely reaction, where in this process we have a kilomole of C2H4. Okay, then we know the epsilon, the extent of reaction is 2 epsilon. Okay, so 100 over 2, we have 50 here. Okay, the extent of reaction is 50 kilomole. Okay, 50 kilomole. Next, the excess reactant, we know that this is being consumed completely, and then we know that O2 is in excess, so it's very easy. Just take this value where we have 100 minus epsilon, okay, equals O2 left. Okay, so what we need to do is just plug in the extent of reaction value, where the value is 50. So we get 50 O2 left. Okay, so the answer for this one is 50 kilomole. Okay, we have 0 here, completely consumed. We have 50 here. Okay, last one we have 2 epsilon equal 2 times 50. So the amount of C2H4O produced is 100. Okay, so here we have 100. So the answer for this is 100 kilomole.